this Origins magazine. So, today I thought maybe I would say something about these articles on evolution. There are two articles on that subject, and one deals with the question of whether or not life could arise from chemicals, and the other one deals with the question of whether or not once you have some living organisms, such as simple cells or something like that, you can have an evolutionary process that produces everything else, including human beings and rhinoceroses and so forth. So, the basic point made in this first article is that in living organisms you have very complicated machinery which is necessary for the functioning of the organism. So what we're talking about here are the bodies of the living organisms. So the whole idea in modern biology is that life is just material. Life is nothing but matter. This is what the biologists are thinking. So they're taking their idea of matter from the physicists. Essentially, what's happened in the course of history is that the physicists started out by giving a description of matter that worked in certain areas quite effectively. Newton was the one who really started this process. So physics became the model for all science. And people got the idea that you're really being scientific if you can explain things in terms of the laws of physics. So this became the basic goal in science. So the biologists who are trying to understand what life is took this up. And so for many years now they've been trying to explain life in terms of physics. Well, meanwhile there have been some developments in physics which are perhaps a little bit disconcerting from the point of view of the biologist, because in recent times at least some physicists have come to the conclusion that in order to understand matter you have to bring consciousness into the picture. This is something that happened with the development of quantum mechanics. So I'm not going to talk about that today, although I'll mention briefly that such people as Schrödinger and Heisenberg, von Neumann, Wigner, and so on have all said that in order to understand what happens in physics, you have to bring in consciousness, which is something non-physical. So there's one biochemist named Morowitz from Yale who made the observation that the biologists are trying to reduce life down to matter, but then the physicists reduce matter down to consciousness. Actually, you can go in a complete circle. The psychologists supposedly study consciousness. That's their field of study. So they will say, well, consciousness can be understood in terms of brain cells and other entities studied by the biologists. So we can understand consciousness in terms of life, namely the brain and so forth. And then the biologists will say, well, we can understand life in terms of chemistry. Especially the biochemists will say this. Then the chemists will say, well, we can understand chemistry in terms of physics. And the physicists will say, well, to understand physics, well, we can understand that in terms of consciousness. So you go in a complete circle. But it's true that only certain physicists think this way. Others will say that this is all nonsense. So you can find controversy in the field of physics. But anyway, let us consider what the biologists are saying about life. They start with chemistry as their basic given structure of knowledge, and then they want to explain life in terms of chemistry. So in chemistry you start out with atoms, which have certain properties. And the basic idea is that atoms can combine together to form molecules in various ways. So the simplest analogy to explain the idea of chemistry is provided by Tinker Toys. So, if you have a set of Tinker Toys, you have short little wooden rods, and then you have little circular pieces with holes in them in various directions. And you can stick the rods in the holes and build up a structure. So, this is similar to putting together atoms to form molecules. In fact, chemists have models of molecules which are very much like Tinker Toys, which you put together different atoms with little pegs sticking out in different directions. And this way you can assemble models of molecules. So, let's say you have a pile of Tinker Toy parts and you start sticking them together at random without any particular order. You just grab them at random and start sticking them together in whatever way they come out. If you do that, you'll see that you get certain characteristic shapes. You'll find the pieces tend to come together at certain angles. And the reason for that is simple enough. The little round pieces have holes in them at certain angles. So naturally, when you start sticking in pegs and pieces and so on at random, you're going to get things that come together at those angles. So you'll get certain characteristic shapes. So, if you do this, you can say, well, look, just by sticking things together at random, certain shapes are emerging. So, if we did this for 1,000,000 years, surely we would get a 20-foot high scale model of the Empire State Building. Someone could make that argument. Because by sticking together Tinker Toy pieces for 10 minutes, we've gotten squares and triangles. So we've certainly made some progress. So if we kept this up for 1,000,000 years, certainly we would get a 20-foot scale model of the Empire State Building. Is this reasonable? Well, why not? What's wrong with it anyway? What's wrong with that?
For one, the Empire State Building is a well thought of structure where there's some parameters. You can see if it's well ordered, where your random sampling of things, there's no possibility for there to be such an order.
Well, as I pointed out, we get order as soon as we start sticking them together, because after sticking together Tinker Toys for a while, you'll definitely see that you get a lot of right angles. Now, that's an orderly thing. A right angle. After all, you have 360 degrees, and one possibility is 90 degrees, that's very specific and orderly. So you're certainly getting order when you put them together. So you just do it for a longer time, and you get more order. Eventually, you'll get the Empire State Building.
Wouldn't you have to prove that after so many random tries that there was an emergence of a set pattern of order that would be repeated?
Well, it's just a matter of time. Given a long enough time, we've seen a little bit of order is emerging in a short time, so it stands to reason that more order will emerge in a longer time, and eventually we'll get the Empire State Building. Yeah?
Is it like your cow jumping to the moon and a man's ability to jump? In other words, it only progresses beyond certain patterns, like in that movie we saw with the British, the BBC, and then King of
the Game of Life.
Yeah. Isn't it the patterns can only develop a certain level of complexity? You get squares and right angles, but you don't get the whole aggregate total of complexity. In other words, you can only progress to a certain level of complication.
Yeah, and there's a reason for that, though. Can anyone say what the reason is?
Intelligence you put in the organization. Or you just randomly throw anything together without the intelligence.
Yeah. Well, the reason is that because of the structure of tinker toy parts, you're bound to get right angles because they're built that way in the first place. In other words, that design is built in to tinker toy parts. But there's nothing about tinker toy parts that specifies the Empire State Building. So it's not surprising that you get simple right angles and squares and things like that. That's throwing together tinker toy parts at random because they're built that way. They'll naturally produce such things. But now the design for the Empire State Building is something quite different. That's not built into tinker toy parts. So in order to get the Empire State Building by assembling tinker toy parts, you'd have to bring in the design from outside. That is, it's not built into the parts. Now you could imagine building a kind of components of some kind which might specify an Empire State Building. Well, let's see how to do it. Well, you can imagine the following thing. You'd have to build pretty complicated components, but let's say we have some balls with holes of different shapes, and we have rods of different shapes. And so a certain kind of rod can only go into a certain kind of hole, and so on. Well, if you set it up properly, you could arrange it so that the pieces could only go together to form a larger, complex structure. So if you kept trying to put the pieces together at random, and if they wouldn't go, you just kept on trying, and if they did come together, you left them together, then with such a thing you could build up that complicated structure. As a matter of fact, suppose you take a jigsaw puzzle, typical jigsaw puzzle in a box, and you just try to put together pieces at random. And if they don't go together, you just keep trying, and if they do go together, you leave them together. Well, it's just a matter of time before you put together the whole puzzle. And the reason that you'll put together the whole puzzle is that the shapes are such that they only can link together in one way. And it was built that way in the first place. So that way you can put together the whole jigsaw puzzle. So the same thing with the tinker toy parts, since in fact they don't have shapes that are designed in the first place so as to specify, let's say, the Empire State Building, there's no reason that you're going to get that if you keep putting together the parts at random. So we can apply the same thing now to life. There's a famous experiment done by a man named Stanley Miller here at UCSD. He took ammonia, methane, water vapor, and, well, I guess that's basic. Yeah, that's what he took. Put it in a big flask and put an electric spark through it for a certain number of hours. And he found that some brownish gunk accumulated. If you analyze that chemically, you'll find that there are certain molecules that are called amino acids. So now it seems that proteins are made of amino acids. There are 20 different kinds of amino acids. There are certain types of chemicals. And proteins are made of amino acids. And proteins are very important molecules in the body. Everyone knows you have to get enough protein, and so on. So immediately people started saying, well, look, this shows that life could originate just by throwing together molecules at random in a primordial soup. The idea was you start with the Earth billions of years ago in a primordial state in which supposedly there's no life. The whole thing supposedly condensed out of an earlier primordial gas cloud surrounding the sun. Of course, the sun also supposedly condensed out of a gas cloud. And the gas cloud itself condensed out of the debris thrown out by the Big Bang, which started from nothing. So this is the idea of how things might have originated. So you start with just atoms bouncing around at random with no order whatsoever in this primordial soup. And you can imagine that there would have been storms with lightning, so lightning would have been flashing through this atmosphere full of different atoms, and amino acids might have formed. So the argument was then that if initially you can form amino acids in this way, after 1 billion years or so, you'll get life. And from then on, evolution will produce everything, including ourselves. And it will all happen simply by chemistry. And that's all you need. So that's their argument. But it's a similar thing. Actually, it's not surprising that you should get amino acids if you put a spark through ammonia and methane and so on, because these are fairly simple molecules. So they're like the small groups of tinker toy parts that stick together to form certain characteristic shapes. It's not surprising that you get those shapes, because the atoms are such that they naturally come together that way. But when it comes to building a cell, like even a bacterium, that's a different story. Because in fact, a bacterium is a very complicated structure. And most people don't appreciate just how complicated a bacterium is. But actually, a single bacterium is looked at as a mechanism, that is, as a machine. It's more complicated than anything human beings have ever built. So therefore, it's hard for us to even understand how complicated it is. Because if you take the most sophisticated computer, let's say, that anyone has ever built, like one of these Cray supercomputers or something like that, that's nothing compared to a bacterium. In fact, so this article is meant to give some idea of how complicated cells are. We have this drawing here, which is borrowed from National Geographic magazine. Don't tell anybody. But actually, this is a much more colorful representation. Theirs was black and white. But these different shapes show some of the things you find in cells. So if you look at a cell, you find all these rather complicated structures within the cell. Now, these are called organelles, and they have various names. There's the nucleus and the nucleolus and the Golgi apparatus and so on. So people have looked at these things through microscopes for many years. And the nature of a cell is that if you look at one of these structures within the cell more closely, the more closely you look at it, the more complicated you see that it is. It's just as if you look at some machine from a distance, it may look like a simple little blob. But when you look at it more closely, you see it has some complex structure. However, if you look at man-made machines, you find that if you look closely enough, you no longer see complicated structure. You just see the material the machine is made out of. For example, if you look at an automobile engine, you'll see that there are certain parts that fit together in a rather intricate way. But then if you look under a microscope, all you see is metal. You don't see a finer layer of structure. Now, if you look at one of these modern computers, like a personal computer, you can go down further and still see structure. If you look at one of the chips in the computer under a microscope, even at fairly high power, you'll still see intricate designs there, because they've miniaturized the circuits. But still, if you look at it under an electron microscope, you will see that the whole thing looks very crude. I don't know if you've ever seen an electron microscope picture of one of these microcomputer chips, but you'll see what looks sort of like a highway system, made of very crude, sort of wavy slabs that go around at different angles and so on. Well, and then if you look at that even more closely, you just see the substance that it's made out of, with no particular structure. So with a cell, at the level of looking at it with an electron microscope, things are still very intricate. And in fact, they're intricate right down to the level of molecules. So And you find very great intricacy. For example, in this cell, this is just a typical sort of cell, here's something called the cell wall. Now right here, this looks just like a slab of something. Well, we have a picture showing what cell walls are like in bacteria, at least. This is a diagram that is supposed to show, in part, what they find. What this diagram represents, these different colored shapes represent different molecules. So essentially what we have here is what you might call a kind of cloth, with fibers going two different ways, just like in cloth, but it's made of molecules that are linked together. So the cell wall is made of layers of this, which wrap around. And this is not exactly ordinary cloth because it has the property that it can grow. And it turns out there's a manufacturing process whereby molecules come together and build up this cloth in a systematic way. Because the cell is, you can imagine, it's wrapped in layers of this, but the cell keeps growing and dividing, so the cloth has to keep growing also. So this is the cell wall. Now we didn't show it, but if you look at each of these little colored shapes that we have here, each one is a rather complicated structure. It's made up of hundreds of atoms put together in a very specific way. So the cell needs this for protection. If you remove this from a bacterial cell, it will die very quickly because it won't be able to survive. A bacterial cell without this wall is so fragile that if you just jar it slightly, it bursts open and it's destroyed. So that's just an example of what happens if you magnify the wall of the cell. So there are these very intricate structures, and there are molecules that perform very intricate operations. So we have this example of DNA, what's something called DNA dirase. I'll just explain briefly what's going on here. You've probably heard of DNA. Well, you can imagine what DNA is. Imagine an extremely long chain which is made of 4 different kinds of links. And by putting the links together in different orders, you can spell out a message. So imagine that there are millions of links in this chain, spelling out a very long message. So in the bacterium, this chain is there, and it's folded up in a very complicated way. The DNA in a single bacterium is several thousand, if you stretched it out, it would be several thousand times the length of the bacterium. So to fit it inside the bacterium, you have to fold it up. So it's packed in with many, many folds. So when the bacterium reproduces, it has to make a copy of this DNA. So it makes an exact copy, and that's quite an amazing process. But one part of this process is that, well, to make the copy, you go down the chain, and essentially you bring in links that match as you go down the length of the chain. So now, once you've done this, going down the full length of the chain, you have 2 chains that are copies of one another. But the thing is, they're folded up thousands of times all together within this very tiny space. Now, you can imagine doing this, say, with strings. Suppose you have 2 strings that run parallel to each other, and they're folded together, folded over and over again thousands of times. And now you have to separate them into 2 places so that they're completely separate. But they start out completely together. Now, you can imagine you might get some problem with tangles if you tried to do that. So, in fact, in the bacterial cell, there's a tendency for the DNA to get tangled up. So, in the cell, there's a way of eliminating tangles. And the method is this. If you've ever tried to unknot a tangle of string, you may see that one string goes underneath another one. And you can see that, well, if only it went on top of the other one, then you could undo the knot. But normally with string, unless you want to cut it, you have to keep twisting around to try to undo the tangle. So the bacterium has a system for cutting the DNA and then re-splicing it. So if you have two pieces that go like this, it can cut the lower piece into two parts. Holding on to the ends, it moves the upper piece through the cut, and then it reassembles the two ends above the cut. So if you have a system like this, it's easy to undo knots. So the cell has a system like that. Now, we made a drawing showing how it might work, showing this little robot here. If you can take a look at this drawing. But it shows the steps you would have to go through to perform that operation. Now, this is fictitious, by the way, this drawing. Nobody knows how it's really done, but they do know that there's a kind of enzyme, it's a big protein molecule of some kind that does this. But you can see, just by thinking about it, what this thing has to do. It has to grab a hold of the two strands, like two ropes, and it has to cut through one of the strands, move the ends apart while holding on to them, because if it lets go, then it'll lose the end, and then it'll be real trouble, because how will it ever find the two ends and bring them together and put the thing back together again? So you can't let go of the ends. That would be fatal. So holding together the ends, you move them apart, then you have to have something that holds onto the other strand and moves it through the gap. And then you have to bring together the first two strands and connect them again. So all those operations have to be performed. So I can give you a challenge. Design a machine that will do that. Just for let's say for ropes. So please design a machine that will undo knots in ropes by performing this operation. It has to cut the rope and move the ends around and so forth. What would it take to build a machine like that? Let's say you have to build a machine out of springs and gear wheels and knives and electric motors and things like that. So if there's anyone here with mechanical aptitude, you could try to actually design and build such a machine. What I propose is that it would be difficult to build it. It would be a fairly complicated little gizmo. So one molecule within the bacterium does this operation. And if it didn't do it, the bacterium couldn't reproduce because it couldn't disentangle its DNA. So that means it couldn't build another copy of itself. Now, bacteria tend to be killed in the nature of things. So the life expectancy of one bacterium isn't very long. So that means if they can't reproduce, they'll die out very quickly. Bacteria manage to keep living because they keep dividing in half and producing more and more bacteria. So there are always plenty of them around. So the result is you can kill bacteria like anything, but unless you kill every last one, very quickly you'll have more. For example, some bacteria can divide once in 20 minutes. So if you start with one, then in 20 minutes you have 2, and in another 20 minutes you have 4, and then 8, and 16, and 32, and so forth. So the point is, without this particular arrangement, the bacteria couldn't reproduce. So how did the bacterium get that arrangement in the first place? Without it, it can't even reproduce and it will die. So it needs that apparatus in order to even live. So you might say, well, it evolved. But unless the bacteria can live and reproduce, there's no question of evolution. Now you might say, well, an earlier kind of bacteria had some different arrangement, so it didn't need biota. Well, you could say, well, by chance, maybe you could. So you can actually try it and see how rapidly you get improved automobiles. And what I'm asking now is not just to improve the automobile, but to add a new kind of machine. just to make it more realistic as far as automobiles go, let us say that for automobiles in northern countries, it would be convenient to have an automatic little snow shovel, snow plow device, so that when you push a button on the dashboard, the hood sort of opens up and this little snow plow thing comes out. And in this way, in the morning, when you find your driveway is completely covered with snow, you just push the button, this plow comes out, and you drive out and you plow your driveway out. Very convenient. So, of course, present cars don't have that. So, by zapping the instructions to the computers that control these robots, could you get such a snowplow device to be added to the car? Now, you can easily see how to design such a device. You need probably some hydraulic machines to move the plow, and of course you need the plow blade itself, and you need different joints with bearings so they rotate easily, and you need some kind of motor to power the hydraulic devices, and then you need some electrical equipment which goes to some switch on the dashboard. So I think an engineer could put together something like that. But now I'm asking whether just by randomly changing the program for these robots that build the cars, you can expect to get something like that. Well, yeah?
Can't they counter that, we're talking about cold steel, and whereas with molecules or organisms, we're talking about things that are breeding, and there already is a possibility of mutation, and there's generations, and there's
well, that's why I use the Toyota example.
You're not comparing apples to oranges. It's not like the robots are breeding, and therefore they can create it from, I understand the example, but that's taking it on a grand scale. I did robots and copying small scale on myself. But just in my neophyte or layman's mind, it just seems that when you're dealing with something soft, it's more pliable, so to speak. But with organic things, there's a possibility of mutations and...
Yeah, but you have to understand, first of all, the reason I used the robot example was that there you have a process that's going on. Now, to be sure, it's going on because there's a big factory and so forth, and they're maintaining the robots. But still, that process is going on producing machines. The robots aren't producing more robots, to be sure. Although you can imagine a robot that builds robots. If a robot can build cars, a robot can build robots, too. In fact, it could build the same kind of robot. So,
small baby robot.
No, same size. It's perfectly feasible. In fact, I'm sure they're doing it already at IBM and places like that for computers. I know they're using computers to control the assembly line process for manufacturing computers. So why not use a computer to control the assembly line process for manufacturing that same computer? And also, actually von Neumann back in the early 50s asked whether you could have a machine that could completely build copies of the same machine. And you can have that. It's possible. Be a very complicated machine, by the way. He designed one and wrote a book about it. It takes an entire book to describe that machine. But it's a machine that makes a complete copy of itself. So, in talking about such machines, you can ask whether by zapping it at random, you can get it to develop new functions. Like I gave the example of adding a snowplow to an automobile or something like that. But you can come up with all kinds of examples like that, of adding a new function to the machine. Now, organic things only look soft and pliable from a distance. That was another point we made later in the magazine, by the way. But if you look at them on the level of molecules, there's nothing pliable about them. The molecules are more like tinker toys, as I was saying. They fit together in very rigid patterns. So, on the level of molecules, it's just like having parts that fit together only in certain ways. And these are like standardized parts. So the question is, can you get a new kind of machinery? Another example we mention here is there's a kind of bacterium called, the name is Escherichia coli. Well, coli refers to the colon. And in fact, in your intestines, you have millions of these bacteria. So in this room, there are probably hundreds of millions of Escherichia coli right at this moment. So, anyway, they're in there. So a bacterium, you've probably seen pictures, it's like a little cylindrical thing. And from the outside it looks very simple. But these cells have a rather amazing thing. It seems that they have what they call flagella. A flagella is like a long strand that sticks out from the bacterium. And it's curved in a spiral. And they can spin the flagella. And so if you spin a spiral thing in the water, it acts like a propeller. So by spinning this flagellum, the bacterium can propel itself through the water just like a submarine. And so how does it spin it? Well, it has a little motor, it turns out. And they've looked at this with electron microscopes to try and figure out what it's like. It seems like it looks very much like an electric motor. It has an axle and some kind of disc arrangement, and then there's some fixed discs built into the wall of the cell, and the discs rotate, and it can go in forward or reverse. So the bacteria can go forward or it can back up if it wants. And these bacteria, by the way, exhibit a rather simple form of intelligence because it seems they like certain chemicals and they don't like other kinds. So they'll swim in the direction of greater concentration of chemicals that they like, and they swim away from chemicals that they don't like. So they manage to steer and do all kinds of things. So anyway, now there's some kinds of bacteria though that don't have this kind of little motor with the flagellum. So let's start with a bacterium like that. Now, let's go to a bacterium that has the motor and the flagellum. By evolution. Okay, it has to happen by accidents, mutations, which are accidental. So how do you go from bacterium with no motor and flagellum to one that has one? What are the steps? So I can give you that as a homework problem. You have the DNA, which supposedly specifies all the different proteins and other molecules in the cell. So, in a cell that has this motor, it produces appropriate proteins that assemble together to form the motor. Now that's pretty amazing in its own right, that they assemble together. It's just like, it's not only that you have a motor, but the parts of the motor have to automatically assemble together to make the motor. Well, that's a good trick, but you can build things that would do that, if you think about it. But just by accidents hitting the cell, how are you going to get that? That's the question. So someone may say, well, it could happen by a sequence of accidental steps like that. So I'm open to that possibility. All I ask is that you specify what the steps are. If someone says, well now, let's not go into that, you should just believe that in fact it happens that way. Never mind what the steps are, you're asking too much. But it's certainly possible. So therefore you should believe that it's so. You should believe that it did come about just by a process of mutations gradually producing this structure. The idea is the mutations produce the structure, and then once the structure is functioning, that gives the bacteria an advantage over the bacteria that don't have that structure, and so then that becomes dominant. So that's called natural selection. So the idea is by mutation and natural selection, it all comes about. That's how the E. coli bacteria got their little motors, and that's how other bacteria evolved eventually to become human beings, and so forth. You should accept that that's how it happens, someone might say. After all, can you prove that it couldn't possibly happen that way? So I'm saying all I ask is that please show in this simple case of the bacterium with little motors how that could happen. Because if you stop to think about it, there are reasons for thinking it couldn't happen. So what are the reasons? Well, for a motor, you have to have, first of all, an axle that can turn. For example, if it's square, it can't turn. So that wouldn't work. So then the axle has to be connected to some kind of disc. And then there are these other discs. But surely not just any disc will do. If you just put together some kind of disc, it's not going to be a motor. If you look at electric motors, you know you have to have coils with magnets that work in a certain way so as to pull the thing around in a circular motion when you put electricity through it. Of course, they don't really know how these motors work. They think it's maybe like a turbine with molecules rushing through under pressure, hitting some kind of blades that spin around. So let's say it's a turbine then. Well, then you have to have blades. So, and the blades have to be tilted at an angle. So, if you just throw things together, how likely is it you're going to get blades that are tilted at the right angle? Plus, you then have to have the molecules coming through at pressure, under pressure, so you have to have some arrangement that will make the molecules go through. Even if you have the blades and the axle, but you don't have the molecules going through under the right pressure, the thing still isn't going to work. And so on. And then, even if you have the complete motor, if it's not connected to this flagellum, then what good is it for the bacterium? If it's just spinning away and not connected to anything, all it does is waste energy. And actually, you can argue that if a bacterium wastes energy, then it will lose out in competition for other bacteria. Here's a calculation you can do. Let's say a bacterium wastes 1% of its energy uselessly, but you have another bacterium that doesn't do that. So that means that the bacterium that doesn't waste its energy, let's say, can divide in 20 minutes. But the bacterium that wastes 1% of its energy can divide in 99% of 20 minutes. And you may think, well, that's pretty close. But then, for two divisions, it's 99% of 40 minutes. And if you go up for about 99 divisions, it comes to within 99% becomes 20 minutes in its own right. So the point I'm making is eventually the bacterium that's a little less efficient will fall behind by one division from the first bacterium. If it's fallen behind by one division, that means there are half as many of them as the first bacterium. So if it's even 1% less efficient, after a certain length of time, there are only half as many of the less efficient bacteria as the other more efficient one, all other things being equal. And then after twice as long as that, there's only 1/4 as many. So that means it loses out if it's 1% less efficient. So how can a bacterium afford to build a motor that doesn't work and wait around for the flagellum to be added?
You can't really have a research and development department, so to speak.
Yeah, in other words, the bacteria can't afford that because they're all, say, growing in your intestines. Because in your intestines there are millions and millions of these bacteria. But if there's one kind of bacteria, and let's say one bacterium in your intestine has somehow or other built a motor and it's almost perfect. The only trouble is it's not linked up so as to actually enable it to swim. So all it does really is waste energy for that bacterium. Well, it's going to die out. All the others will outcompete it, and it won't be there after a while. So there are reasons for thinking it can't happen. And you may say, well, these aren't perfect reasons. Maybe somehow it could happen. Maybe there's something you didn't think about.
So that means more or less that every mutation has to be a success.
Well, you can have failure.
You need to have a rapid turnover like that because it's just a margin of ability to fall behind.
Well, you can say, you could have mutations that are failures and they fall by the wayside, but someone could argue, well, if you wait long enough, you're bound to get one that is going to be successful. But then the question is, how long do you have to wait? Well, let's say, and this is another basic point, let's say you have to wait 10 minutes to get a mutation that gives you one particular kind of part you need. Let's say 1 out of 10 does that. But then to get another part that you need, it's another 1 out of 10. So that means you wait for 10 to get the first part, but then you have to go through 10 of those cycles to also get the other part, going 1 out of 10. So that's 1 out of 100, you see. And now if you have a third part you also need, and it's 1 out of 10 for that too, then you have to go to 1,000 to get that. So the problems multiply. They don't just add. So, let's say if you need 100 parts, and it's 1 out of 10 chance of getting each part, and 100 parts are needed for the complete machine, then you multiply 10 by 10 by 10 100 times. And that's how long you have to wait in order to get all 100 parts. Yeah?
Could we say, without how you estimate it, if you take a one cell whatever, your symbol is one cell, and you compare it to how many changes would have to be there for a human being or a human form, you couldn't calculate how long that would take? How would you possibly do it?
Well, if it's by chance, for example,
in other words, is that sort of the argument that we have around long we have in the world that's existed long enough to even have those possibilities?
It couldn't possibly happen by chance. That you can definitely say. Because, like this number 10 to the 100th power, that's a very big number. A billion is 10 to the 9th power, so a billion billion is 10 to the 18th. And a billion 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 is 10 to the 27th. So keep going until you get up to 10 to the 100th. So, that's so long that it makes a billion years just like nothing. You know, if a billion years is a long time, think of what a billion years is. Anyway, the Big Bang people will say that the universe has only existed for 20 billion years. So that's nothing compared to a billion years. And if you're talking about putting things together by chance that are of any degree of complexity, then you have to have a billion years or something. In fact, you can do ridiculous calculations, such as the following. You can say, suppose you take the entire volume of the solar system and you divide it up into little cubes, and each cube is as big as a hydrogen atom. And in each cube, a billion times a second, you try to throw together a certain complicated machine by chance. And you do this for a billion years. Well, if the chances are less than 10 to the 100th power, you're still not going to get one. So you can do calculations like that. So chance is completely out.
What do they say we say that? What do they counter with?
Well, they'll say, look, it doesn't happen just by chance. You go through a sequence of intermediate forms, and each step producing a new form is fairly probable. This is what they'll say. So you go by one small step, and that's fairly probable, and once you've got that, it's better for the organism, so that becomes established. And then you make the next small step, and that's fairly probable, and then that becomes established. And then you just go by small steps that are fairly probable. That's how they would argue it. But then the question becomes, well, what are the steps? And the problem with complicated machines, or even fairly simple machines, is in each step the machine has to work if it's going to be selected by the organism. So can you build a machine up going step by step, starting from scratch, and at each step the thing works? Well, no one has shown how to do that with machines. And you can say, well, we just haven't thought of how to do it yet. Surely it's possible. Or people will say, well, I know you can't do that with man-made type machines, like wristwatches and automobile engines and computers and radios and so on. But it can happen with biological machines, because they're different. So, okay, but how are they different, and can you show that? Because as I was saying, there are reasons for thinking it can't happen. The reason very simply is that all the parts, in order to work in a complicated way, have to come together in a specific fashion. And one part will have to relate in a specific way with many other parts. That means in a machine, if you change one part, you also have to change many other parts in order for the whole thing to keep working. Just like in a wristwatch, if I say I want to change one gear wheel, then I have to change a lot of other gear wheels, and so on. So that's the reason for thinking you can't do that with machines. So, But if someone says, well, biological machines are different, so it can happen with them, then, well, how can it happen? What are the steps? So one can argue like that. So that's some basic point concerning evolution. Now that's all negative, however. In other words, one is just criticizing the theory that it all comes about by molecules coming together by chance. So then what do we say? Well, of course, our proposal is that there's an intelligence behind the design of these machines. Our point would be that just as man-made machines are built using intelligence, in which somebody thinks out how to build a machine and then they build it and it works, similarly, these biological machines were built by higher intelligence. But that intelligence had to be something that existed before there were physical organisms, that is, organisms with bodies made out of matter. Because we're saying that there had to be intelligence to build the organisms in the first place. So that means some non-material intelligence has to be brought in. Now, someone could also argue, by the way, that you can't say that this intelligence would have to be infinite or all-knowing or something like that. All you need is a non-material intelligence that has, maybe as good as human intelligence or something like that. You don't need to bring in God. Just some non-material entity that's fairly smart. That's all you really need, someone could say. In fact, Hume, there's an English philosopher named Hume who argued that amongst other things. He was very fond of putting forward atheistic arguments. So one was that if you say that for the design of organisms you need intelligence, surely you don't need an infinite, all-powerful intelligence. Just a moderate intelligence will do. So one can argue like that, but still, the point is you need some intelligence which existed before you had embodied entities. So that's a step. So we would suggest then that in order to understand what's really going on with life, you have to go to some kind of non-physical intelligence. And so that means you have to look in the direction away from just matter, but in the direction of something more subtle. So that's a suggestion. Of course, we would say also that in order to understand God, just looking at material arrangements is not enough. And of course that is stated in the Bhagavad Gita also, that after many births and deaths, a jnani, that is a person who's trying to just use the manipulation of the mind in order to understand everything, will eventually come to the point of surrendering to Krishna, and then he will obtain actual knowledge of God. The point is that even if you manipulate your mind in a very intelligent way, you'll never have sure knowledge of God. But you can get some idea that maybe there's such a thing as God. And the point then made in the Bhagavad Gita is that a jnani, after doing this for millions of years through many births and deaths, because you accumulate intuitive experience from lifetime to lifetime, even if you don't remember your previous lives. That's what's involved here. So after many millions of years of trying to figure it all out using the mind, eventually he will realize that the only thing to do is surrender to God. And then you can get knowledge from God. In other words, by the power of our minds, we can't actually figure it all out. But God can reveal himself to us if he wants, because he has all the power. And Krishna says that he will enlighten us and reveal himself to us if we cooperate with him. All he asks is a little cooperation. So Krishna says, as they surrender to me, I reward them accordingly. So that's a higher principle for obtaining knowledge about ultimate causes of things. But there's a tendency in the conditioned living entity for the living entity to try and figure it out using his own power. And so people speculate about how life might have come about. And at the present time, in our Western civilization, people have developed physics and chemistry and so on. And so they're thinking, well, maybe we can understand life in terms of physics and chemistry. And this has become a whole doctrine, which of course is a very convenient doctrine because it enables you to eliminate God from the picture. And then there's the whole psychology of why people want to do that. But anyway, so, well, I should certainly stop there at 6:26 already. Yeah?
In the case of the bacteria, the one type that's not as advanced, and they have hypothetical flagella on the back and more motivating. Okay. My question is, are they saying that the more advanced type bacterium has evolved from the other type?
Yeah, everything is evolved, and you start with nothing.
Okay. Second point, are we saying that there's no such thing as mutations?
There are mutations. What we're saying is that they're not going to create higher order. Certainly there are mutations, and you can demonstrate that. Normally they produce various kinds of defects. And, for example, they've been mutating fruit flies for years now. You can produce mutant fruit flies with all kinds of different strange things, shriveled wings and bulbous eyes or no eyes and so on. But they have not produced a single strain of fruit flies by mutation that can survive in the wild. In other words, if you take some of your mutant fruit flies and you say, well, here at last I think we've gotten some that are an improvement over regular fruit flies. So
better mousetrap.
now we've got a better fruit fly by mutation. Because fruit flies reproduce very fast, and people grow them in big bottles, feeding them with rotten bananas and so on. So, and then they expose them to radiation, which produces mutations. And they've been doing it for many years now. The whole science of genetics practically was based on the study of the fruit fly and the mutations. Because it also turns out a fruit fly has very big chromosomes in its salivary glands, so you can study the chromosomes and so on. So anyway, if you take some of your mutant fruit flies, you may say, well, now we've got a fruit fly that's probably better. So it's easy to test that. You just release this kind into a cage with normal fruit flies and let them reproduce and see what happens. If this new kind of fruit fly is really better, then after a few generations, you should find this kind of fruit fly in the cage and not the other kind. Or at least it should be holding its own with the other kind. But that doesn't happen. They just die out. And the wild kind are the kind that you have in your cage after a couple generations of fruit flies. So they haven't produced an improvement. Mutations tend to weaken the organism.
So are there natural mutations, or are they all man-made?
Well, in one sense, they're all natural, because...
You know what I'm saying.
Yeah, well, it happens in nature. They used to be called sports of nature, or freaks. That's what they used to call mutants. And it happens, typically you just get some monstrous thing. Or else it can be very subtle, you get just a slight change. But, and sometimes the mutant can be helpful in a perverse sort of way. For example, there's sickle cell anemia.